Welcome to the session 2 of series digital circuit design using VHDL. In this in this session of this series, I'm going to cover some basics of VHDL design, right? VHDL language. So we call this as VHDL primer. So primer means that everything, but I will try to cover the maximum I can. Okay. So before that, let me deal with number systems. Okay, number systems. Sorry, typing mistake. Okay, now when we deal with the what comes natural to us as number system is a decimal system. In a decimal system, we have got digits which are 0, 1, 2, 3, and so on, 4, 5, 6, 7, 8, and 9. So in using these 10 digits, we are able to represent any number. Now this is not how the computer works. In case of computer, there is a binary number system where you have got 0 and 1 as the input. So this is called binary, and this is called decimal. Again, typing mistake. So this is called decimal. Okay, now if we deal with numbers which are binary, then a number might become very big. For example, I can say 0 1 1 0 1 0 0 1, right? So now this is going to be a 8-bit number. Okay, so for the ease of representation, though the computer just understands 0 1 zeros and ones, for the ease of representation, we can have these bunched up into bits of 4. This is called a nibble, right? So now I can represent this 4 digits, which means there are 4 binary digits, means there are 16 numbers here, right? 16 numbers are possible here. And so this set, right, from 0 to 9, right, then you have A, B, C, D, E, and F. Okay, so this is a hexadecimal number, right? So this will be called hexadecimal. Okay, so now this hexadecimal number can be represented. So for example, this can be represented as, so this is equivalent to a 6 and this is equivalent to a 9. Okay, so this would be the hexadecimal number. Now there is another grouping which I can do for the same number. Okay, so this 8 bits can, or rather I would say 9 bits, can be split up into these, which are 3 bits each, right? Okay, so now this would be called 1, this is 1, this is 5, and this is 1 again. So this is known as octal number. Okay, so in octal number, the digits are going to be between 0, 1, 2, 3, 4, 5, 6, and 7. So that's the octal number. Now, so that we don't get confused, there is a certain convention. So if I want to represent, I will represent binary as this number, right? So then I will be following the bits, right? So I could write this as, so this is a binary number, this is a binary representation. Now I can also do 0x, and then I can say 6 9. So this is a hexadecimal representation of same number, hexadecimal. Okay, or I can just do 0 1 5 1. So when I put a 0 leading 0, that means that is an octal number. Okay, so these are the number system and their representation. Now what are their equivalents? Now this one, right, is 69, right? Rather you would say, how much is this? So the way to convert it to decimal would be like this. So if this is the number, right, so this will be 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6, 2 raised to 7. So you just multiply the base with this number. So this would be basically going to be, so 2 raised to 0 is 1, so this will be 1. Then these are all zeros, then this will be 2 raised to 3 is going to be 8. 8 into 1, that's 8. then this will be 0, and this will be 2 raised to 5, right? That's 32. 32 into 1 is 32 plus 64, right? So this is 64. So the total number is going to be equal to 40, 60, 104, 105. So this is the decimal representation of 105. So 105 is represented as this number, right? Now hexadecimal number, we can do the same thing. In this case it will be 16 raised to 0, 16 raised to 1. So this 16 raised to 0 is 1. 1 into 9 is 9, plus 16 raised to 1 is 16. 16 is 96. 96 plus 9 is 105. So that's a decimal representation of that same number. Now the next thing is the octal number. The octal number is 151, right? So 151. So this is going to be 8 raised to 0, 8 raised to 1, 8 raised to 2, right? So this will be 64. This will be 1 into 0, 1. So this will be 1. This will be 8, 5, 40, and this will be going to be equal to, let me see if this conversion is correct. Octal conversion 151. Okay, 5 is a 40, 8 is 64. Okay, so 64 plus 40 is 104, plus 1 is 105. So this is the decimal representation. So what I have shown you is how to convert a number which is a binary number, or a hexadecimal number, or octal number, to a decimal representation. So it's easy to go from binary to hexadecimal or to octal, right? Because you have to just pair these bits, right? While going back, you have a base of 16 in hexadecimal and base of 8 in octal number. So this is about the number system. Usually I'm going to use a hexadecimal representation for all my digital designs. So this is number system. So now this is out of the way. Now let us go ahead. Okay, now with number system out of the way, okay, let's start with what is a hardware description language. HDL stands for hardware description language. Okay, hardware description language. Now earlier, to communicate circuits from a company to a vendor, okay, you need to specify a circuit. Earlier they used to use a pictorial representation, used to be called schematic, but then schematic used symbols and their interconnections, and everybody is coming up with his own symbol, right? So it became confusing after some time. Second, when the circuits grew bigger and bigger, it was difficult to understand what part of the circuit is doing what, right? And it spanned over multiple pages. So this representation was difficult to communicate. So then people came up with the hardware description language to communicate the circuits. Later on, this hardware description language was also was put to a simulation to simulate the behavior. So that was the rise of HDL, to represent and simulate a circuit. Later on, this was the circuit was mapped to a real hardware, right? So that's how it came into being. Now there were two languages that were growing independently. One was called Verilog, and this Verilog originated from a C language. So basically the background is it originated from C. Now if you originate something from a language which is a C language is a procedural language. So Verilog more or less looks like a procedural language. Inherently it is a sequential execution. So inherently Verilog is sequential. Now to specify a parallel block, you would have to put all your concurrent statements in parallel block. So let me try to explain you what is sequential and what is concurrent. C language, or let's say C++, this is mostly used for microprocessors. Okay, microprocessors are sequential devices, like they compute something and then they compute next thing, they compute next thing, so it's sequential. So all these statements which you write in a language are sequential, so the language is sequential. And the device which you target is a microprocessor is also sequential, right? Now in case of VHDL, okay, which stands for very high speed integrated circuit hardware description language, GUAGE. Okay, so very high speed integrated circuit hardware description language. So that's how you call it VHDL. Now VHDL came from a language called ADA, and this is a concurrent language. So the hardware, so concurrent means that all the statements are going to be executed based on events rather than in the sequence in which they are written. So this is called a concurrent language, right? So now this is going to target something which is a parallel hardware, like for example FPGA. Now FPGA is a programmable hardware, or it is also known as FPGA is also known as field programmable gate array. Now the funny thing is there are no gates inside it, but it's called field programmable gate array, right? So why is it called field programmable gate array? Because it can be programmed in the field by a programmer. It can be programmed while it is embedded in a system also. So field programmable gate array, it is a configurable hardware. Okay, in this FPGA, okay, there are lots of blocks which are called configurable logical blocks, or CLBs, right? Now these CLBs, okay, there are many of them, right? There is a huge sea of these configurable logical blocks. Okay, so you will find a big array of them. Okay, so that brings the parallel nature of the hardware. Unlike a microprocessor which has a data flow path and which is a singular data flow path, so everything has to be done in a sequence, right? This has a parallel hardware. Then this is connected using lots of wires, which you also call bus. Okay, so which are running crisscross, just like the roadways. Okay, so these are connected to each other, okay, using these buses. Okay, so this whole thing is known as a fabric, right? So CLBs are connected using these buses or wires, and wherever they meet at crossroads, like for example here, let me change this example here, right? This is a crossroad. This is called switching matrix. Okay, so basically what you are doing is you can interconnect these CLBs by using switches, and the switches are at each cross connection, right? So this is a switching matrix, so you can make a hardware representation by using CLBs, and then there are switches which are programmed so as to make a proper connection. Okay, so this hardware is called a FPGA. Apart from this, it is going to talk to the outside world. So the way it talks to the outside world is through these IOs, or input output pins. So they are over here. Now these are not just simple input or outputs, they are programmable. So these are called programmable IO. Okay, so the next thing which comes here is a programmable IO. Okay, so and then there are CLBs, or configurable logic or CLVs, right? So these things, they comprise what is called a fabric of a FPGA, right? So that's a FPGA. Now, if this hardware is massively parallel, then you need a language which is parallel, right, or concurrent. So that's why you use something called a VHDL or a Verilog kind of a language, which has a provision for concurrent statements. Okay, concurrent statements are not executed in the sequence in which they are written, but they are based on certain events, right? So when an event occurs, the statement is executed. While in case of C, C++, or let's say Verilog inherently is sequential, then the sequence in which you write the statements, that is the sequence in which they are executed. So that would be called programming. So this side, which is going to be sequential, okay, sequential group of statements. Okay, so this is called a program. While if you say concurrent group of statements, concurrent group of statements, okay, this will be called a code. So if you see, if you say code means you are writing concurrent statements. If you write sequential statements, that will be called a program. Now in VHDL, it's inherently concurrent, but then there is a block, a concurrent block only, right? This concurrent block houses all the sequential statements. So this is called a process block. So process block in its own is a concurrent statement, but inside all the statements are going to be executed sequential. So that's the provision here. And same thing over here in case of Verilog. Okay, there will be the statements which are sequential, but to put the concurrent blocks, you use something called always, and then there is a block, right? So this is always repeated based on a certain condition, right? So that's the basic difference between VHDL and Verilog, right? Now there are lots of things which were different, right? For example, in Verilog they used to have something called standard delay format, right, which later was adopted in VHDL also to specify the delays, you know, the signal delays, right? So then it became easy to for a VHDL to use a Verilog block, right? So these two languages could, you know, mix together. So still what happens is most of the test benches are written in Verilog. So test benches, and these test benches are written in Verilog because they are more or less sequential, right? Test benches in Verilog. While you write a circuit, okay, circuit are more or less concurrent, okay? So circuits are in VHDL. Okay, why circuits are in VHDL? For example, let's consider a circuit. Okay, so this represents a circuit, right? So you have got inputs A, B and C resulting in output Q, and then there is an AND operation, and then there is an OR operation here. Now the three signal flows, they are concurrent, right? They are not sequential. So A flows and B flow and C flows, they all flow together, right? So this is a combinational circuit, and combinational circuits have to be concurrent. That's why VHDL is very natural to combinational circuits, while sequential circuits are like, you know, flip-flops and stuff like that. There is a sequence of time, right? So it more like, you know, Verilog is more you know, more close to a sequential circuit, while VHDL is more close to a combinational circuit. So that's why we are going to do a VHDL development later if the time permits. In this lecture series I'm going to cover Verilog, but this is just to get the things out of the way, that why am I choosing a language which is called VHDL, right, and what it stands for, where it originated from, what target device it's going to use, right? So this is Verilog. Okay, Now once this is out of the way, let's look at some other things. Okay, a code. So in the previous session I showed you a simple all logic gates in a code, right? So let's say I have an IC. Okay, very simply it's a 555 IC. Then it has got VDD, ground, and then you have got threshold. Maybe the numbering is not correct, but bear with me. There is something called okay, charge discharge pins, right? And then there's something called trigger, whatever. So there are a number of pins there, right? So this is the outline of an IC which has got 8 pins. This is outline of an IC. This outline is usually written in VHDL as an entity. It's a block of code which defines the outline of a circuit. So that is called an entity. Okay, now what does this circuit do? Okay, what a circuit does. Okay, this is known as architecture. Okay, so this would be known as architecture. So any component, okay, a component has two aspects to it. One is the outline or the ports, right? Then the other aspect of it is what it does, functionality. Okay, so outline and ports are defined by what is called an entity, while what is functionality is a architecture. Okay, and the pair of this would make a component, right? Now a component declaration is one thing and definition is another thing. Okay, see what happens. Okay, if I define something called a component, right? So if I define a component, I have defined an entity and an architecture, but then this component has to be instantiated. Okay, this component has to be instantiated. So for example, I can say full adder. Then I have instantiated component like F1, F2, F3. These are all full adders, but then they are components. So the component cannot be used on its own. It has to be instantiated. So when you instantiate, you can also define entity architecture pair at the time of instantiation. And this is done by a script called configuration. Okay, so you define for a given instance, okay, so for just 1 second. Okay, so for is hanging for what reasons? Bear with me. Okay, fine. So for an instance, I define, okay, for an instance configuration for an instance defines entity architecture pair. Entity architecture pair. Now what does it means? Okay, what it means is I can, okay, have an entity which is an outline, but then I can have multiple architectures. So I can have architecture 1, architecture 2, So I can have two different description or three different descriptions of an entity. Okay, so that there can be same functionality, but they are defined differently, right? So I can decide for a given instance of a component which ones to pair. Okay, now if there is only one architecture, then naturally it will be one pair of entity architecture. But if there are multiple architectures for a given entity, then you have to write a script file which would tell which pair of entity architecture you should use for which instance of the component, right? Now, why there are differences? Because there are styles of writing architecture, right? So it can be a behavioral style, it can be a data flow style, it can be a structural. Just 1 second. Okay, it can be structural. Okay, so you can have a entity which has architecture which can be behavioral, data flow, structural. Now, if I don't have a script like configuration, then it will have the entity paired with the last compile architecture, right? That's what happens. If you have a configuration, then for any component you can define which entity architecture pair to consider, right? Okay, so with this out of the way, okay, let me define some more things. Okay, so we have seen an entity, it's an outline of a component, and then we have seen an architecture which is the functionality. Okay, so these are called primary, this is called a primary design unit. So this will be called a primary design unit, while this is a secondary design unit. Now, a primary design unit can exist on its own, it doesn't need a secondary design unit, so that's why it is called primary. While a secondary design unit cannot exist on its own, it has to have a primary design unit. So architecture is a secondary design unit, while entity is a primary design unit. Now, if I have, so let me just check something. Yeah, if I have like, if I was to write a code, right? So it is a very good idea to be able to reuse your code, right? So it has a very good idea to reuse your code. Now, to reuse your code, you need something called a library, and this library may have packages. Now, how do I understand this? uh, Very simple. You go to a library of a college, right? So you want to basically read some books, so you go to the library, right? So now what happens is, in the library, how are you going to search for the books? Okay, the first thing what you're going to do is you're going to look for a section, right? For example, if you want to read a book on mechanical engineering, you will look for a section which is called mechanical engineering. Then similarly, you have something called a section called a chemical engineering, right? Now, so you would go to a different section, right? Now the two departments may have same topic, right? So for example, let's say fluid dynamics, right? So fluid dynamics may be there in mechanical also, and fluid dynamics may be there in chemical also. Now there may be a difference in treatment of them, but they are still different, right? So there should not be a conflict that you are going to refer to a fluid dynamics in chemical engineering, but you have picked up a book from mechanical engineering, right? So this conflict has to be avoided. That's why you have separate sections or department wise. So that is what a package is, right? So in case you have something which is common, okay, but it belongs to different packages, right? So there is no conflict, right? So that's why there is a concept of packaging. Okay, so packaging means that you have a library but then you have grouped these functions, procedures, constants, and let's say components in a small unit called package. So multiple packages are going to make a library, just like multiple departments make one library, right? So something similar. Now, so we were talking about primary and secondary design units. So package is a primary design unit, and then there is something called package body. That's a secondary design unit. So package on its own can exist. It's a block of declarations, while if you have to define something in a package, you need a body for it. So that is called a package body, right? So a package can stand on its own because it's just a declaration, while a package body is something which depends on a package. So for example, let's say I have declared a function in a package, right? And but that is not defined in a package, it is defined in a package body. So now if you have declared a function in a package, you would need a package body to define the function. So declarations are done in a package and definitions are done in package bodies. Similarly, if there are constants, for example, which are called deferred constants, so you have declared them in a package, but then you have given them a value at a later stage which is deferred, right? So that would be put in a package body. So package body is a secondary design unit, while package is a primary design unit. Configuration I will consider as a primary design unit. I can write a configuration, but I may not use it. That's why I'm calling it a primary design unit. So let's bunch them up. Okay, so you have a primary design unit, and then you have secondary design units. Okay, so examples of primary design units are going to be entity and package in configuration. Okay, secondary design units are going to be architecture, package body, okay, so that's the secondary design unit. Now, so once we have defined this, we can go ahead with some more terminology of VHDL. Okay, so VHDL is a code, not a program, because the statements are concurrent, right? Then you have understood that. Then a VHDL has got design units like entity, which is the outline of the components, architecture, which is the functionality of the component. Then you make a library which has got number of packages. Packages are declaration. Now the declaration of something declared in a package would be called a package body. And when you instantiate a component, okay, you can decide the entity architecture pair, right? That would be called, okay, configuration, the script file. Now again, for a given entity you can have multiple architectures, right? Architecture can be behavioral in nature, data flow in nature, or structural. So what do you mean by that? So architecture styles, architecture styles. Okay, so these architecture styles can be behavioral. So how do I do that? So for example, I have got these inputs A, B, and C in. Okay, so I can bunch them up as one line, which is called select, right? So I can say select is basically a bunch of A, B, and C in, right? So now A, B, C can take values, right? So these values can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So these are all possible values of the inputs. So let's consider a full adder, right? A, B, C in are the three inputs, and then the output is Q, which is, or rather, I would not say Q. There are two outputs. One is sum, other one is carry. Okay, so these are the outputs, right? So in this case the outputs are going to be, so for example, if I take sum, okay, so I have to take all the odd parity as 1. So this will be 0, this will be 1, this will be 1, this will be 0, this will be 1, this will be 0, this will be 0, and this will be 1. So this is all odd parities, right? And the carry is going to be so in case of this one, okay, so there is going to be 0 carry here, 0 here, 1 here, then it's going to be 0 here, and here it's going to be 1, here it's going to be 1, and here it's going to be 1. So this is the carry. Okay, so this is known as a truth table, as we have seen in the other series. This is called a truth table. This is some kind of a behavior of a circuit which is known as full adder. Okay, this is known as full adder. Now how would I do this in case of a VHDL? So first I will write an entity. So let me also follow this convention. All the keywords are going to be blue colored. So I can say entity full adder. So full adder is a name. Full adder. Then I can say is. So this is a keyword. Then I can say port. So I'm going to define the input output pins, right? So in the port I have got A, comma B, comma C in. Okay, and then they have some kind of a input output mode. So that would be, let's say, in. So in is also a keyword. So let's put it blue. In. And then its type. Let's say type is std underscore logic, which I will come very quickly. And then there is a semicolon. And then I will say there is a sum, which is an output, and then carry is an output. And it has again the mode or the direction out, and it has a type std underscore logic, and then bracket close, and then you have a semicolon, and then you are going to say and the name of the entity is full adder. Okay, so this is how you have written the entity. Now let's go to writing an architecture. So the keyword is architecture. Okay, and the name of the architecture is, let's say, FA. Then of the entity which is full adder is architecture full FA of full adder is, and then you are going to write another keyword which is called begin. And in this begin you are going to define. Okay, so what you're going to do, you have already, you want to bunch up, right? So you would write here signal. I will come to what this is, signal. Then there is a signal which is called select, right? And then this select is, okay, signal select, and this is a special kind of a signal which is bunch of 3 signals, right? So signal select std underscore logic. So this is the type underscore vector, and this is 1 2 no sorry this is 0 to 2. Okay, semicolon. Okay, now what I'm going to do here, I'm going to say first of all I'm going to bunch them. This is called aggregation. Okay, select is assigned A, comma B, comma C in. Sorry. Okay, so I have done that. Now I can say sum is assigned. Sorry. Sum is assigned something, right? So what is it assigned? It is assigned 0 when, okay, when cell is equal to, and then you're going to write what this cell is. right? So cell is equal to 0, 0, 0. Else, so else is a keyword. Else 1. So when is also a keyword. So just 1 second. When is also a keyword. So let's put here when. One, when select is equal to 0, 0, 1. Else, so else is a keyword again. Else, and so on. So basically, so on. You keep on defining that till you reach the very end. In the very end, the last statement, I'm not going to do anything, just put else at the end, and then it is going to be assigned 1, which is for the condition 1, 1, 1. Okay, so this is a behavior, right? This is a behavior. So if I define a behavior as a truth table, right, then this style of writing would be called a behavioral architecture, right? And then at the end, what you have, and the architecture name is FA. Okay, so you see the code is very simple. You define the outline and then you define the functionality. So while you are defining the functionality, right, what are you doing? You are defining the behavior. So this style of architecture is known as behavioral architecture. I could have written it differently. I could have also written it this way. So this is, let me write down, this is a behavioral architecture. BEHAVIORAL, behavioral architecture. Now next I am going to do a what you call data flow. Now what data flow does is, using some statements, I just show the data flowing between input and output, and what is the relationship between the various signals, right? So I can write it this way. Okay, I can say architecture. Now I have to give it a different name, so I will call it FAD, so as to distinguish it. So FAD, okay, is sorry, of a particular entity. So let me write it clearly. Of a particular entity. Now this entity is called, it's called the same entity, right? It's called full adder, right? Full adder is, and then I'm going to have begin. Then what am I going to do inside the begin? I'm going to define the functionality. I'm going to say sum is assigned. So by the way, this is not a full adder because I have defined one statement as sum, but what about carry? So I will define the carry same way. Okay, so carry is assigned 0 when cell is this much, and so we will follow this truth table. Okay, when cell is this 0, 0, 0, 0, 0, 1, and so on. So we will define carry. So there will be another statement for that, which is again behavioral. So you are writing two behavioral statements, for one for sum, one for carry. Now in case of data flow, I am going to do the same thing. Okay, but in this case I will define it differently. Sum is assigned. What is the sum assigned? Sum is assigned A, then there is a keyword called XOR, then I am going to say B, then I'm going to say XOR, and then I'm going to say C. So there is a flow between A, B, C to the output sum. Similarly, I can say carry is assigned, okay, A and, so and is a keyword, A and B, and this is in a bracket. Okay, then I can say A and B are with B and C, B and C, then I'm going to say or with, sorry, B and C in, sorry, not C, C in. So let me do this clearly, people get confused. C in, or C in and with A, C in and with A, semicolon, and then you'll say and the name of the architecture, which is FAD, and semicolon. Let's see what happened over here. Yeah, so FAD will be black colored, just because trying to mix the. Okay, so now this architecture this style is called data flow. What is happening is A is XORed with B, XORed with C. These are all incoming signals, rather C in. Okay, so these are all incoming signals, right? So this is kind of a data flow between input and output. So that is why it is called data flow architecture. Now let's say either can also be represented as XOR gate and then another XOR gate, right? And then there is a C in, and then you would have this going this way, and then this output, okay, is going to be, so this is going to be the sum, right? So hang on a second. Okay, the sum of A and B, that's going to go as a AND with A. Then this sum is going to AND with B, and these are going to OR, and this will be carry, and this will be sum. Now this can also be written as there is a half adder. So I have got A and B, and then the output of the half adder is given to another half adder, in which it is given as C in. Okay, and then the carry output of the half adder and the carry output, so two carry outputs. Okay, so this is sum, and the two carry outputs are given to a OR gate, and that makes a carry. Okay, so this intermediate signal is S0, right, and this is C0, and this is S, so this is sum, so I don't need to label this, and this one is C1, and this one will be C1 ORed with C, so that will be carry. Now if I was to represent this, okay, then I would need to instantiate two half adders, and then there are intermediate signals. So I will write this here. So I'm assuming that there is a component called half adder. Okay, so let's write this architecture. So we will write it as architecture, and then I would say FAS of the same entity, full adder. Okay, full adder will be black colored, sorry, this is the name. Full adder is, and then you will have signal. So intermediate signals I will define. In this case I am having S0, C0, C1 as std underscore logic. Then I can say begin, and then I can instantiate HA. Okay, and this HA would be of type half adder. So this is a subcomponent, and then in that I would define port map. So let me just put here port map, and I will map the pins. So in this case I have input as A and B, and then the sum comes as sum, sorry, not sum, it comes as S0. So if you remember, there is an intermediate S0, and then this comes as C0. Then you have, this is HA1, then you have HA2 is again an instantiation of a component called half adder, and then this is a port map. So let's make this as blue colored, PORT space MAP. So again you do PORT space MAP, and then you are going to write here sum S0 Cin gives out sum, and then it gives out C1, right? So this is a structural definition, right? A and B are the two inputs, and S0 and C0 are the outputs of half adder. Then in the second half adder, S0 and Cin are the inputs of the second half adder, and sum and C1 is the output of the second half adder. Then you can write that carry is assigned, okay, is assigned C0 or with C1, and then you'll say end FAS, sorry, FAS, right? Okay, so now this definition, okay, where I am taking components, mapping their inputs and outputs, so this would be called structural style. Okay, so we have got an architecture style which is behavioral, we have data flow, and then we have structural style, okay, so of writing the same full adder, right? So one entity, three architectures. Now when I instantiate a component, I can define which one to use. Now if you have learned about the earlier session on digital circuit design using ADS, I've shown you that this particular configuration is the best in terms of delay, right? So this, when I was doing full adder in that series, I've shown you that this configuration is the best when it comes to delay. Okay, so when you instantiate a component, you decide which architecture you want to. If it is time critical, I'm going to use data flow. Internally it will be executed like 2 XOR gates and 3 AND gates and a 3 input NAND, so 3 NAND gates and 3 input NAND gate. So this I have already covered in the other series. This is faster. Okay, so here what I conclude here is there can be multiple styles of architecture. So at this point I'm going to stop for this series, this session. In the next session we will cover more components, right? So let's say